Okay, let's get started. This is the first lecture in the new semester series in economic engineering. And as the old saying goes, every battle is lost or won before it's begun. So we're going to start our battle. And what I want to do with this lecture is just lay the groundwork that we all understand what economic engineering is about and what it's not about. My experience is that if you go in this with the wrong expectations, and it's quite easy, it takes like half the semester to reset yourself. What I also want to do is work through sort of a toy example, just to give you a flavor of how this may go without all the necessary details to understand precisely what's going on. So I want to take away this feeling of, well, this sounds really great, but I mean, you can't do it anyway, so because economics cannot be modeled by laws kind of thing. Okay, so those are my goals for today. We'll have, we'll do first, well, we have first an hour, and then a short break, 10 minutes break, and then we'll finish off with another 45 minutes. So I'm going to write it down what we're going to be doing. And it's called economic engineering. Now, what's important about this is the engineering.
Can you guys see Max?
Yeah?
Me too.
I can see myself. You can't see me?
Oh, it's more.
And who's the count?
Yeah, Max is good.
I can see your, I don't see. Maybe I should leave and come back because I just see your display picture.
Since you joined, we can't see Max anymore.
Wait, I'll be back.
No, but what should we do? Huh?
No,
What?
the rest can you see?
No, but Jaap, can you see me?
No, I can't. You know, I mean, you're on Koen's account and you could, and we just see Koen's picture.
Oh, we need to spotlight Max, perhaps.
Yeah, spotlight him.
I will spotlight Benny.
Yes, now I see you.
Yeah,
You're spotlighted.
yeah. You look beautiful today, Max. Go ahead.
This looks like the Cuomo brothers. They only have this silly banter on CNN, huh? You're not supposed to be talking when I'm lecturing. Now, will you shut up? Huh?
Okay, well.
All right, you have to cut this out of the recording, okay? Okay, this is what we're going to be talking about, and I've underlined the word engineering because, perhaps perversely, I first want to emphasize what economic engineering is not. And it is not economics. So, why did I spell that with an X? It is really engineering. So, perversely, an economist has the greatest trouble understanding what we're talking about, okay? I'll talk a little bit more about that. There's also a field called econophysics. But it's also not physics. Right. Now, physics is obviously a little closer to engineering, but in some essential parts, it's quite different. The physicist aims to describe the world the way it is. Okay, so he looks at the stars, he looks at some quant, or he imagines the quant, he actually can't see it, and he tries to describe exactly what they're doing, and then he's either right or he's wrong if the thing behaves the way it he models it to be. He thinks it to be. So he sets up his laws. All right. Now, this is very much in the spirit of how economists will work as well. So they look at the economy or they look at some kind of economic system, and then they model it, and then they're either right or wrong. Okay. This is patently not what an engineer does. All our models are wrong. We don't even care whether they're right or wrong. Are they sufficient for the purposes that we designed them for? Okay? And also, we don't really look at nature and try to model it like a star. No, we try to build our own nature. So we try to build a car or we build a robot, and we design it in such a way, that's called engineering, so that it behaves according to the way we want it to behave. Right? So the picture we would have as an engineer is that we build our own reality, and this is what we call a system. And then this thing just does what it does. It could be an airplane, it could be this, it could be that, right? Now, to make it do what you want it to do, you come and study in this department, and you will learn that to make the thing what you want to do, you build a controller, and that controller moves the system so that you get some desired output, right? And then you learn further things, and if you feed this back, then you can do a closed loop and blah, 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 okay? Now, what you see here is already something quite different from both economics and physics, okay? So a physicist doesn't have a controller. He doesn't imagine that the star is moving that way because there's a controller that he has designed. No, he just has this one system that he looks at, right? Now, economist works the same way. He wants to model an economy, and what does he do? He just says, okay, this, that, everybody together, the government, the central bank. Okay, there's one big system. There is no division between a system as the object of study and the controller, which is the way you want to make that thing move, okay? This is a particular engineering perspective, and you got to take this perspective, okay? So if somebody asks you, well, I get asked this question a lot, how do you know what you're going to be doing is correct or true? I say, well, I don't really care. It just has to work, okay? So I design the system for my purposes, whether it's some economic system, and then I make it in such a way that I can control it and make it do what I want to do, right? Is this thing correct? No, maybe not, maybe yes. Who really cares? Is it sufficient for the purposes that I am designing it for, okay? And then the other comment you may get is that, okay, engineering and physics are different because in economics we have a lot of human actions and you can't model those and therefore you can't do this kind of stuff. Now that is also not correct. And the solution lies in this way of looking at it, okay? So if you design as an engineer a car or an airplane, it is not correct that there are no human actions. There is a pilot in the car and there's a pilot in the airplane and there's a driver in the car, okay? So, but what do? You don't model that driver. You make a model of your system, which here is the car, or an airplane. And there, you'll make a controller, right? Now, you can put a person there, but you can also design an autopilot. So it's a very different way of looking at it. Suppose this is the entire economy, then you can think of this as some description of the economy. And what would the controller be? Well, that could be the central bank, or it could be the government, okay? But you keep it separate. Don't model it with it, all right? If this is a business, then this guy here would be management, So if you have your supply line, you would model your supply line different than whatever policies you have in order to implement that, okay? If you have a bank, you would model the credit process and the customer base or whatever you see as the system separately from your decisions to raise the interest rates or lower interest rate or expand the credit, etc. So when you do economic engineering, be aware that it's always engineering, okay? Decide what your system is, then decide what is the controller, what are the little knobs you can turn, decide what is your output, what it is you see, what are you interested in, and you put it in that framework, the input-output framework and the controller framework. So again, an economist or a physicist will never look at the world this way, okay? But we do, all right? So this is a fundamental difference to start off with, okay? Now, there are many other differences, and I want to list some of those. And after I'm done listing all these differences, I want to start talking about how we can approach economic problems using engineering tools. Now, if you study economics, say you go to Rotterdam and you get your degree in econometrics, you'll find that you're learning something that looks like math, but has nothing to do really with the way you're trained here to do engineering. Now, if you look at it, most of it is some sort of statistics. So they have piles of data, they fit this data, they make regression lines, and it's all kind of data-driven, what we may call black box approach. Now, of course, we do black box modeling here, but it's really not the tradition. The tradition is what we would call a gray box approach. A gray box approach, we mean that we first start off, if you want to model some car or airplane, you start first going like, okay, this is a mass, this is a spring, this is a damper, this is this is that. I know the various laws that govern these things. Let me put it together as a preliminary model, and then I'll, somehow fit these parameters, and then I'll try this thing out, okay? You don't start saying, okay, I have this car, this system, let me make a gazillion measurements of what it's doing, and then try to fit some regression line to it, okay? So this is what we would call a gray box approach. Gray box, why? Because there's always noise and other things that we don't model explicitly and we throw in at the end, Otherwise, I guess it would be a white box. Now, this is not what econometrics does. There are very few laws, if any. It's all data-driven and uses these keywords like big data and everything and tries to fit data. Now, a lot of business also works along these principles. So if you start studying this as an engineer, you is like a total separate field. You'll learn all this stuff, and then what has this got to do with your course in statics, strength of materials, thermodynamics? It seems almost separate. Okay? So that's what it's not, economic engineering. So we do very little black box methods and as little statistics. And the kind of statistics we do is not really statistics, it's more probability theory. Okay? There's all kinds of, yes? Again.
Would you call the opposite of data-driven, model-driven?
Yeah.
Model-based.
Model-based, right? Huh?
First principles. First
principles, huh? We don't really have a name for it because that's what everybody does. I mean, remember your first year, you learn statics, you learn strength of materials, you learn this, you learn that. I mean, and then somewhere is a course in statistics somewhere that everybody tries to forget about that they even have to do, right? So what you got to see is it's just not in our tradition to think that way. And if we think statistically, it's an afterthought, and usually only in control theory, all right? So we say, let's put some white noise on it, and then we have some uncertain stuff. Huh? And there's a good reason for this. I mean, I have this smartphone in my pocket usually. Now, this thing got designed by a bunch of engineers. Now, I ask you, do you think it's possible to design such a thing using just regression lines? I don't think so, okay? I don't think you can make a car that way. You can't even make a bicycle by doing a bunch of data fitting, okay? The predictive power of these type of techniques is too low to make an engineering model, okay? So there's a good reason why we don't do it, because I don't think if you go and think about an engineer designing something in a way that he can predict what the behavior is, it's just not a fruitful technique to use. It's more of a descriptive thing, so you can describe what happened in the past, but these models are fraught with all kinds of danger when you try to predict the future with them, Huh? As the old saying goes, all these models are true until they're not true anymore, Huh? So My experience with them trading on the markets in New York has been always that guys who started off with this, they would go well for a while and then they would just blow up and never knew why they blew up, all right? Because the models just, they work and then something changes, but you don't really have any insight. Okay, so I think for the purposes of describing an overall economy, this may be okay, but not for designing things. So in economic engineering, I also do not think that the black box approach is a fruitful one to get going, If alone because you'll be trying to compete with people that are doing this, and what's the point? You want to do something totally different. This is engineering, so go to think like an engineer, right? Huh? Now, economics is a rather broad field, and econometrics is not the only thing. You have a lot of business economics, and these guys, the thing about business, what's good about them, they actually have to get something done, which is very different than economists. It's better they don't do anything, because otherwise they may be wrong, and then it's not so great to publish papers, okay? So this is true not just for economists, by the way. But business guys, they got to make the business run. So interestingly enough, they use very little like classical economics. And what they use quite differently than an economist will use it. But they have tended to develop their own models. So if you talk to them, they have all kinds of Excel sheets that are huge. They may use some accounting tools. So these are, again, separate pieces of software, separate theories, mostly based on addition and subtraction. So, and a lot of ad hoc modeling techniques, okay? Now, most of these ideas are extremely fruitful, and they're important to understand, but the way they solve it is just not something that you can use as an engineer, right? So somebody gives you an Excel sheet and says, here's the model of my business. How in heck are you going to design a controller based on this model? I mean, what are the inputs? What are the outputs? What are the states? I mean, you'll be lost, It won't even be possible in principle. So whereas or if you get a set of accounting, a general ledger or a profit and loss statement from accountants, how are you going to make a controller based on that, okay? It's hopeless. So somewhere, what we need to do, if you take an economic engineering approach to how businesses do, is to kind of understand what they're doing, and believe me, that's a very difficult step, because they really know what they're doing, and they've been working for years in this industry, and there's a whole tradition, so they have their own terms. And what you got to do is understand enough of it so you can translate these into economic engineering terms, and then when you make your economic engineering model, then you can design controllers, and you can do the whole little jig that we're so used to and doing, and what you've been trained to do, okay? So it's also not business. Then there's another area called finance, or finance, depending if you're British or American. That is also not economic engineering. Now, some of you may have had a course in finance. I think you have had one, Brit, huh? Or no, you had? Yeah, a minor in finance. So what department gives this? The math department, I believe, right? Huh? Yeah. So these guys, they have a very mathematical bent. So they tend to prove theorems. And interestingly enough, the type of mathematics they use is quite different than the mathematics that we use as engineers. Most of engineering mathematics grew traditionally out of the 19th century in attempts to do geometry, because the geometry fits well with the kinematics of motion. And then, of course, Newton's addition in how you can think of forces as the reason why these geometrical placements are are happening. We call it kinematics, the geometry of it, and then we add on that the driving forces, okay? Mathematicians do not have such a tradition, okay? So they may pull a differential equation out of thin air and just say, here it is, okay? And this is now modeling, I don't know what, stock prices. And you go, oh, okay, and then you can prove the existence of a solution and things like that. Very different tradition. And interesting part is, if you look at the type of math they use, you just don't see much familiar stuff. I mean, we like to see things with a sine and a cosine, you know, because that's movement, or distances, you know, x is a distance, and we have units behind them. Now, the mathematicians, they don't really bother about units very much, you know. I don't think they even mention what it is, or if you ask them, they wouldn't know. And the complex numbers that are just so cool and familiar to us, I don't think they use them. They consider that old math. Right? Now, the basic issue you're going to find is they'll write an equation, and every time there is a parameter, they'll use a Greek letter, and every time there's a variable, they use a Roman letter. And these things, you can kind of imagine what they are, but these things get a little fuzzy, you know. So beta may be a market beta, alpha maybe, you know, there's some kind of market alpha, you know. Those of you to finance, they know actually that these things all exist. They use the entire Greek alphabet. Volatility is, I think, sigma. But if you ask them what is volatility,
That one we used as well.
sorry?
For volatility, the standard deviation. We also used sigma. That's the only one corresponding.
No, but it's not the standard deviation. This implied volatility is different than the standard deviation. Only under certain conditions will they prove that it may converge to the standard deviation, okay? But it's not equal to it, all right? So this is how they will proceed. They'll posit that there is something called volatility. If you ask them what are the units of this, they won't know. They will have to think really hard. Then you would say, what is it? They say, well, we don't know. And what they will really do is we have an equation, in this case is the Black-Scholes equation, and if we know what to plug in the equation, we can calculate what the volatility should be, but we don't know what it is, okay? It's called implied volatility. And then it's a number, and if these models sometimes get implemented on the financial markets, then guys have to say, well, yeah, that doesn't do me any good. So they'll set up something that in their eyes cuts close. So they'll have something, I think on the Chicago, they use this thing called the VIX. And it's just some number, some averages of some prices, and they calculate something, and that all of a sudden is the volatility, not the standard deviation, okay? All right? So the problem with these models is not only that the math is quite different, but you see it's sort of a top-down approach. So you say, okay, this is the model, and now, okay, and now let's see, so what they typically have is a solution looking for a problem, you know, which is kind of the opposite what an engineer will do. He will first have a problem and then find a solution, okay? But these guys is different. They first have some model, and then they start looking around if they can find a problem to fit their solution. So you see quite a different approach to how to go about it. And these things become very fuzzy, so in the end, they are not useful to build the stuff on, but what you got to know, what you got to do is you got to be familiar with this. So when you build your own model, you can say, well, in the context, what is the concept, in the context where I'm working in engineering probability, what is the concept that gets closest to their notion of beta and their notion of volatility, you know? You know, like if volatility is the up and down movement, then maybe it's the frequency, in the frequency domain that gets close. But maybe they mean the amplitude, right? Maybe they mean a combination. You don't really know, but you got to figure it out, all right? Okay, now the Black-Scholes equation is formally, I mean by that mathematically the same with a change of variables as the heat equation. Now the heat equation is something engineering. That's how heat moves, okay? Now, if you know what heat is from your lectures here, you could make that connection, right? And then you could say, well, this is the temperature, or this is this, or that is that, right? And then you can say, okay, now I have a definition, an engineering definition for what volatility is. This is the one I'm using, and with this, I'm going to make my model, right? Now, whether this is the same what they do or not, that is not really the question. The question is your model good enough for engineering purposes to actually use this in a particular problem? All right? Okay? So the message of these guys is they turn the world upside down. They have a top-down approach, and we have a bottoms-up approach. They come with a very large, generalized model, and they see how they can apply it. We take a problem, say a big car with wheels and four wheels and a spare wheel and I don't know what, right? And the first thing we do is make a unicycle model. Yeah, why? Well, you can see what the center of mass is doing, right? And a couple of things. But then we can't figure out whether it's going to crash in the wall because it's broad, so we need to add a couple of wheels. So maybe we make some kind of dual, and keep adding stuff in order to make it more realistic for the problems we are solving, okay? All right. Now, then there is kind of the last kind of what I want to treat last. That is what you would call the classical and neoclassical version of economics. Now this is what you typically get at school, right? The secondary school, the high school, and it's one of these courses that you tend to ace if you're mathematically inclined, because the math behind it is so simple, and the people who are more interested in the economics, they tend to be a little weaker on the math, so they get stuck there and they can't get a good grade. And you can get a good grade without even understanding what's going on. That's usually the experience of engineering students. Whether this is correct or not, or morally right, I want to leave in the middle. But the experience is that you get a high grade without even knowing what's going on, right? Now, in a sense, this approach is the closest to engineering as you'll get. And this is the approach that we are going to build our ideas on. Now, most of engineering uses laws from physics. It is not physics, but we use these laws to make our own designs, but we base it on laws. Now, if you think of mechanical engineering, what is like the law that you would base everything on, right? I would venture to guess that's Newton's second law of motion, and we usually write it this way, okay? This is like the beginning of mechanical engineering. Without this law, this tells you what a force is and how it's related to motion here through the acceleration, okay? Now, this was your kinematics. Now, and this tells you why it's happening, so now you can do dynamics. So this here is our workhorse. Now, if you go back in time and try to remember what you learned in this course in economics, you'll learn nothing of the sort. Huh? Nothing. Nobody said F is m times a there, right? Huh? So what did they say? Well, I would venture to guess that when you're pushed, you might remember this figure here. It's a demand and supply graph. Okay? So this will be a demand line. This will be a supply line. This is the price. This is what they would call the quantity. I would even go so far as if you ask somebody on the street if you give some picture of what economics is all about, this may be something that would come to mind. And if you ask somebody what mechanical engineering is about, he would say something about Newton's laws or something, F is m times a, right? Now, The question I want to now try to answer is, what do these things have to do with each other? Now, on the face of it, not very much, all right? But I think they do. And the insight in that little thing makes everything run, okay? So this is what I want to now spend 15 minutes on, is just imparting to you this insight, why this is the same as this. All right? Now, normally an economist would put P here for the price. And he puts a big Q here for the quantity demanded, but I'm not going to do that. I'm going to put a V here. All right? So think of the volume. Huh? Economists or finance people will use the word volume for the volume, what we would call the volumetric flow rate. The volume for us is like a number that's associated with the contents of a box or something, or any kind of closed three-dimensional shape. But if you say the volume on the stock exchange, you mean really the volumetric flow rate, okay? So how fast is this volume moving, okay? Now, let's call the slope of this line. Now, this is the supply line. The demand line goes the other way. But you can make it go this way by just flipping the sign of the volume here. This is also called the quantity demanded. And mostly in business, they will call this demand. But economists will call the whole phenomena demand. All right? Now, the first thing you do when you're, I would ask an economist, if you're an engineer, well, what are the units of this, right? Now, I've talked to I talked to one Nobel Prize winning economist, and he couldn't answer this, okay? He says, well, I don't really know, but most of the time, he said, this is what we would call a flow variable. So this would be, say, an oil, barrels of oil, or apples. Okay.
What was the question that you posed to the economist? I didn't get that.
What are the units of this variable here and this variable, right? Okay. Now let's talk first about the price. What are the units of price? It's a little easier, right? So suppose I'm buying apples, then what are the units? Some euros, or I'll just use a generic word, per apple, right? That's what you would think. Now, interestingly enough, if you open up one of the most popular texts in economics that gives an introduction, the introduction to supply and demand, these are apartments, and this is what they call the price of apartments. But the price of apartments for them is a rent. Now, a rent doesn't have this price. A rent would have $1 per apartment per month, which is not the same. Okay? Now, this is an exception, but it happens often enough. Usually, they think of it in this are the units, right? And certainly in business, I think this will be the case, as you will be able to attest, yeah. Huh? The price is just in euros per item. Okay. Now, the next thing is, what are the units of this demand here, this quantity demanded, all right? Now, if you're not careful, you will say, well, these are then, if this is an apple, then these units are apples. Now, that's incorrect. That's not how they look at it. Because demand for apples is not like, so you bought 50 apples and now I'm done with apples, okay, for the rest of my life and the rest of anybody's existence. No, it's a per day kind of thing, okay? So the demand for apples is like, your demand for apples may be 1 a day or 2 a day to keep the doctor away, all right? But you don't keep the doctor away by just buying 50 apples and then be done with it, okay? So the units here are so many per day or per month or something like that, right? Again, there are exceptions, but that's usually what you mean. Okay, when you say, what's the demand for oil? You say 500 barrels. But you don't mean 500 barrels and then everything is over. No, 500 barrels per what? Per day, per year, per hour, per, huh? Usually that's left out. But be careful, right? Okay? All right, so sometimes they'll do this differently and sometimes they do this differently, but on the whole, you know, how do I get rid of this? Oh. These are the units, okay? Now, what are the units of this? These are newtons, and these are what? Meters per second squared, right? So that doesn't do as much good yet, eh? But I think if you now do the following, actually, you know, there's something interesting. Newton actually never said this. This is what we always say Newton said. Newton actually did two things. He first took a law that's called the law of the momentum law, and this he got from a friend of his, Huygens, who got it from Descartes. Huygens is one of these names that you can only pronounce if you're Dutch. Otherwise, if this was a true, if I were a true English speaker, I would say Huygens or something. And this doesn't come from Newton. This is just the definition of momentum. All right? And then what Newton said is that the force is the change of momentum. That's what his second law is. And what people have done, especially engineers, they've taken this law, plugged it in here, and then said that this is the second law, okay? And that's what we know it as the second law, all right? But really, this is one statement, and this is another statement. And it's important to go back to this. Actually, you know, interesting enough, Newton didn't even say that. What Newton really said, if you read him, and I've read him, it wasn't easy, is this. Okay? He says the change of momentum, he says, well, he didn't have the word momentum. He said the change in the quantity of motion, that's what he called it, is equal to the force, right? But what we now see, the force is the rate of change, but he saw this. This is what we would now call the impulse of the force. This is what he called the force. This is what he really said. But that's an aside. Now, if we look at this law, things are a little clearer what may be going on here. I mean, you could be so bold as to assume that momentum, since it's a P, is the same as a price. Okay? All right? Then you can say, well, this velocity then would be corresponding to this quantity demanded. Now that feels right to me because this is in items per day. Suppose I'm selling cloth, right? Then this will be meters of cloth. And suppose I'm selling it per second, right? It's kind of ridiculous. This will be then in meters per second, right? And the units would totally correspond with the units of a velocity, okay? So that's a nice starting point, I think, and very intuitive, because what are you doing here as an engineer? You're just looking at something else that's moving at a particular rate, whether it's apples or meters of cloth or something else, okay? And that you call the velocity. Okay, okay. So we got a way of looking at the quantity demanded as an engineer, we call it the velocity. Then we say, all right, let's look at this velocity. What does Newton tell us? He tells us that it must be ever proportional, this is his lingo, to the momentum. All right? Now, what does a supply and demand graph tell us? That the quantity demanded is ever proportional to the price. So I can take this law and just claim, as an engineer, that it's totally parallel to the law of demand. There's no problem. All right? Now, what is the mass? That is just the slope. That's called the price elasticity. Why? because the mass is equal to dP over dV. So how much does the price change with the change of the quantity demanded? That means how elastic is the price, okay? It's actually the inelasticity, because it's the inverse, huh? But we don't worry about details. So we see that inertia, elasticity is this change that it becomes easy, but inertia is really the inverse of that, and it's the engineering concept that says to you, well, you know, here the price doesn't change very much. It's very hard to change, okay? That means there's a big force on it, okay? So it's very inelastic, all right? And then this is then just the price, all right? Now, what you don't want to do now is get too philosophical and say, well, is this really true? And no, a nice idea, and now I want to think about this, because it doesn't really matter, right? I mean, all you want to do is take an economic phenomenon that is well established in the law of demand and somehow describe this in a law that we have, and if it works, it just works, okay? And then you just have to remember that momentum is the same as price, okay? Now, this has been tried before by making these analogs between economics and mechanics, but they always did it a little differently, and I want to spend a little time about saying why this is the critical step. So what we have here is this is like mechanical engineering, and this is economic engineering. And as momentum is now parallel to a price. Okay? Now we also know that a force, that's the rate of change of the price, is going to be the rate of change of the, is going to be this. All right? Now, we will call this a want, and I will explain this a little later. All right? But before I do so, let me first lay down the intuition for why this is correct. Now, you will see that in a lot of the existing treatments, price is considered to be analogous to a force. So here's the idea. You say, okay, these goods are moving, and why are they moving? Because there's a price difference, right? Because somebody wants to pay for it. There's a price. So price is the thing that's pushing these goods, all right? Therefore, price is is analogous to a force. Right? It's very tempting to argue this way, but it happens to be wrong, right? Now, how can you most easily see that this cannot be the case? And I think the easiest is to see that you know from mechanics that in equilibrium, the forces have to balance out to zero. You cannot have a net force, okay? If you have a net force, you're going to accelerate something, and that acceleration is going to give you a reaction force that is exactly equal to this excess force, you know? So you can never have an unbalanced force. Now, that means if the net force is zero, that in equilibrium, the net force is zero. If the force is the price, that means that in economic equilibrium, all prices should be zero. Now, we know that that's not true, right? You just have to go and think around for 1 microsecond and walk around your grocery store, and you definitely will not find that all prices are zero there, right? So this is not right. So the economic engineering perspective is that in equilibrium, the change in the price is zero. So in economic equilibrium, you get price stability. All right? This is the correct way of looking at it. All right?
You say change in price, and it's change in price over time.
Yes. Yeah, because that's how the, yeah. So remember, this is the definition of a force, right? So it's a change in price over time. The force is precisely the change of momentum in time, right? So whatever an economic force is, it has to be a change in price in time, and the thing is in equilibrium if the economic forces, the net economic forces are zero, right? That doesn't mean that individual particles are not accelerating. You just need a reaction force that something else is decelerating to push itself against, okay? But if you look at the center of mass motion of a complicated system and there are no outside forces on it acting on it, the thing must be in equilibrium and the total momentum cannot change, okay? This is actually Newton's first law. He says a body at rest goes at a constant speed, right? And that means there are no forces acting on it. So in his first law, Newton lays out what he means by equilibrium. Okay, he means in equilibrium there are no forces. In the second law, he defines what he means by what a force is. And the third law, he tells you that momentum is conserved. And now we begin to the things where all the implications come out. Okay? Now, if momentum is price, then a force must be a change in the price. And some force, the only effect that you know has to be a change in the price. Okay? In fact, that's how we define an economic force. So this thing has an interesting history because before Newton, there were, of course, ideas what a force was. The word is much older. And we had, I mean, you already know in Dutch we have a word kracht, which is also old. I mean, it's not like energy, which is a newer term where it's always the same in every language. It's an old Germanic word, okay? So people had these concepts, but they never knew what a force was. So they knew there was this force, and they're pushing, and they're pulling, and they were imagining all these forces. And interestingly enough, what they did was they only imagined it on Earth, and they called that a sort of terrestrial force. So Aristotle had some theory that if you drop something, that the force on it at a certain point was constant, and it was dependent on the kind of material. You know, like air would have a tendency of a force to go up, and heavy things earth came down, and water was in between or something, and you had all these notions of force. And then they looked at the sky, and then they had God sitting there as a sort of a force, totally unrelated to what was going on Earth. And they went on, and then they had ballistics, where because they like to kill each other, they try to figure out how much force they would have to put in a cannonball for it to go. And they had all these different theories: celestial mechanics, ballistics, terrestrial mechanics. It was all a hodgepodge. And then Newton comes along and says, okay, guys, you know what? I'm going to define a force to be this. If you know what a spring, what the force is, well, just attach a mass to it and see how it's accelerating the mass, and then you will know what the spring force is. If you have a damper, do the same thing, right? Okay, then he says that somebody came along and said, well, this thing is, let this object drop and it gets a constant cruising speed, and you're saying that F is m times a, it has to accelerate. So what does Newton say? Well, there must be another force. Let's call it the friction force. So he just keeps answering all the problems, and he turns out to be right, okay? Then he sees the planets moving in circles, and somebody says, yeah, so if your law says you go in a straight line, but this thing is not going in a straight line, and there are no forces acting on it, right? I don't see anybody pushing. Kepler, interestingly, he had angels that he imagined flapping his wings, pushing these planets. I mean, it's almost ridiculous, but this was a clever man. I mean, he was famous. Yeah, he has a drawing of some angels going flap, 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 right? And Newton, he sees the apple fall apocryphally, and he says, no, it's the force of gravity, and this is what it is. So everybody says, hey, wait a minute. So you mean the moon is falling, and he said, yeah, the moon is just falling. It's just falling in such a way that it doesn't kind of catch up with the thing it's falling against, and it just keeps going around in a circle. But it's still just a force, and it's the force of gravity. And here's the formula for the force of gravity. And everybody goes, oh, okay. Huh? Now, that's a nice unification, right? Huh? So the critical idea is always this. Know what is a force? Just look at the change of momentum. If the planet is changing its momentum, and it's just, instead of going a straight line, it's going like this, there must be a force. Let's go look for it. Okay, I don't know what it is. I don't see it. I can't feel it. But I see a big Earth there, so let's just call it gravity, right? Huh? You figure it out, you add the law, and there you go, you're happy again, right? That's the game. And then something critical happens. And that's what I think is the real value of this piece of insight for economics. There was a clever guy, and he said, I forgot his name. Maybe I never knew the name. He says, well, I studied these planets, and there's one of these motions that Kepler never got right, you see, because it doesn't go in an ellipse. It does this weird bubble in it, right? It does this. So your law is wrong. So then another clever guy says, well, I think Newton is right. Let me calculate if there are indeed only gravitational forces in the universe. Let me calculate if there were another planet that's causing this, its gravitational field will be causing this, where that would be. So he went ahead and did that, and he realized that that planet is doing that you couldn't see it under normal circumstances because it's behind a bunch of stuff. But a special day, he calculated you could actually see it. So sure enough, on that day, all these guys with big beards, they put their telescope there, and yeah, they saw it. Discovered a new planet just based on his laws. That's the critical point. Then you go like, okay. Now this thing has got predictive power, you know? What Kepler did, he fitted a bunch of data, I would say, without exaggeration, 11,500 years of data, okay? They were looking at these stars since the Sumerians, so we're talking 10,000 BC, okay? He was able to fit that, but he wasn't able to predict the existence of another planet. It's only when you get Newton's law and the definition of a force that you go in a different domain, okay? And then some handy engineers go, they say, well, if we can predict where a planet is, I can predict what this piston is going to do in my car, and I can do this. And these guys went running, and they made themselves a lot of money, you know, in the Industrial Revolution, using Newton's principles, you know, to make machines. And they improved humanity quite a bit, okay? It's all based on this idea that whatever the force is, this is how you define it. Okay? This is the critical idea. So, thinking that price is a force is wrong. Huh? Yes, Chit.
Yeah, the units of price were dollars per unit, right?
Right.
So, what are the units for wanting something? Is that dollars divided by unit squared?
No. Huh? Let's say this. There's momentum, there's a price, there's the units are this, right? Huh? This is a good question. Huh? I only said no because I like the question, and I immediately want to put everybody on the right track here. What do we know? We know this, right? Okay? So what are the units of P dot, right? Now, Chit, I'm sure you don't have to think very much to realize that it's something like this, right?
Yeah.
Huh? Okay?
Yeah.
So it's not dollars per unit squared. No, it's dollars per unit, per day, or per year, or whatever it is. However, if this is equal to dp dt, right, then this is a price change per unit of time, so it must be this. Okay? Similarly, P the price must be the sum integral of all these forces, right? Okay?
Yeah.
All right? From minus infinity to some moment t, and then you'll get the price at that moment in t. This is precisely what you would do in engineering, right? So you would say, well, what's the momentum? Well, I have this big car, and my car's not working, I gotta push it, so I get a bunch of people, and they start pushing, they start applying a force, but just applying a force and walking away, that's not gonna make the car move. You gotta apply the force over a moment in time, and then the car will pick up momentum, right? Huh?
Yeah.
This is precisely what you do. I came from minus infinity, but it didn't matter. I started pushing at the particular moment, and then I pushed in the force. Applying a force is like flowing in the momentum, okay? So you see this car, and it's filled with momentum, all right?
Yeah.
Okay? That's Newton's idea of a force. So what does a spring do on a mass? It just keeps pushing, and it's pouring momentum into that mass. And where is it getting the momentum from? From the wall. And where does the wall get it from? From the earth. And then the earth moves the other way, except you don't notice it because it's so big. Okay? That's the picture. Now, what is the economic picture of this? It says, well, what is the price of any good? Well, in some degree, in this way, you got to say it's the accumulation or the accrued value of all the little things that you've done before to, to make it come out that way. Now, if you look at Adam Smith, and you read that, that's also hard to read, you'll see that he has a definition of price, and he says the price is the toil and trouble that you have to make in order to get this price, okay? So they were slightly less sophisticated than we are about prices, huh? But he did think it through, and he says, okay, this is what's sometimes called the labor theory of value. So that things only have value because you have to put labor in it, you gotta work, you gotta add value, and this is a value adding process, right? All right? So you see the price as built up in these increments of f dt, you're adding it to the price, okay? Now, this sounds like whoop, but it really isn't, like the old saying goes, if you wonder whether it works, you go and see whether they tax it. So there's a tax called a value added tax, right? Belasting toegevoegde waarde. What is the value added? That is exactly this. This is a marginal piece of value added, and you just keep adding it to get the price. All right, now if you do a tax, then you're just putting another force here where you're taking away a little bit, like a friction force, when you're pushing the car, huh? Then not all the momentum will go in the car, some has to go in the wheels and the bearings and other things, right? You like to keep that as small as possible, huh? So the government actually also uses this notion of price when it does taxation, huh? Okay? Is that clear? There are other places where you use this. There's the future markets, and you look at this, say, is a futures price. And they'll say the futures price, so this sometimes they call the futures price at moment t, is equal to the spot price, so at 0 to t of the cost of carry. And that's what you do. You say, well, what's the price of oil or wheat or these products a year from now? Well, I can do two things. I can either make a contract to buy it a year from now, or I buy it now, but then I'll have to pay all these costs in order to store it, and that's called the cost of carry, and then I have the same thing. So you see that the futures price has to be a formula like this, okay? So this notion of price as a value-added thing is all over the place. It starts with Adam Smith, and it ends with taxation and futures and that kind of stuff, okay? Again, what for an economic engineer is important, and I want to now take a break, is to see ram this in your head, this relationship. This is the definition of price, okay, as a time variable. After the break, I want to talk about prices as value, like a future, just present values. There's other notions of price, but this is the time domain economic engineering definition of price. It's always this, no matter where it comes from, all right? And then if you want to know what the relation is between demand and supply, what do? Well, you can draw your demand and supply graph. Here it is. Here's a supply line. Maybe you're here. And you want to move over here. So I'll just draw this little vector. So the price has to change. That's the force. And then the quantity demanded has to change. That's the acceleration, right? So per unit of time, I'm asking for demanding so many more apples, or selling in this case, this is a supply line, and I'm jacking up the price at this rate. This is also called the force of demand, and this is just called the expansion of demand. So this is the force of demand, and this is the demand expansion or contraction. So this is another thing about economic engineering. They will use quite different words. In this case, they actually use the word force. And but you can just see it, okay? But this could go like this. Such a thing is also called a movement along the demand line. And then when they draw something like this and they're over here, I mean, what does that really mean? Well, it means that, I don't know what this means, but that means there's another mass that has this inertia, and somehow they're colliding or interacting with each other through a spring, I don't know what, to make sure that at this point that force is zero. So it's not moving from here, and hence the price is constant, and the quantity, the volume on the market is also a constant. All right? Okay, I want to take a break right now, and then see you back in 10 minutes, exactly at 1:45. Okay? Dus je wat on demand?
Wegen over de supply line, toch?
Ja. Ik vind het altijd leuk om terug naar de basis te gaan. Ik weet niet,
ja, ik heb vorig jaar ook wel meegekeken. Dat ik echt een aantekening.
Ja. Ja, dan... En dan ben je helemaal in de war en dan zeg je van wat kracht. En het is een heel vreemd gevoel. It's just a funny feeling. You can do all of mechanical engineering almost without forgetting what the definition of a force is, okay? But the problem is when you want to do original research, this is when you kind of get stuck, you know, your mind goes every which way and you don't know how to discipline it anymore, you know. So taking this time to go back to the basis is very fruitful, you know, to deepen your understanding, very, very fruitful. But this is just the idea from this lecture is not to understand it all. I don't want to do that, but I do want to impart what the basic way of thinking is, the principles, okay? And so this is what this is all about. We're going to go through Newton's laws and exactly say how they correspond to various economic things. And it's very good to treat this in a kind of excruciating detail. But before we do, I just want to get this picture, you know, of a force as being a price change. And it's the want, your wants or your desires, if you want. The word economists use is a want. And it's approximately equal to a desire, but a desire is something really strong. It's like a strong force. The want is a more generic term that you can use. We'll talk a lot more about this. Why a force is a want. We also call it sometimes just an economic force. Or just a force, who cares? Sometimes even an effort. But this is the intuition that's behind it, and we'll make that clear. I did want to now move on a little bit and say that, okay, on the one hand, we have a conclusion that what this gives us is an idea of economic equilibrium that to correspond with Newton's idea of rest, right? So a balance of forces. Now this is important, right? So Newton's first law says that if there are no forces, so no net forces acting on a body, then it will go with this constant speed. And the law of demand has this idea that you have a demand line, a supply line, and somewhere where they cross will be the equilibrium price. And in a sense, the time derivative of the equilibrium price is zero, right? So that's the idea behind it, and this is how you see how this is the case. Now, these forces can come from a variety of sources and do not have to be necessarily a crossing of supply lines, whatever this even means, okay? All right? So this is some collision situation. We'll talk about this all a little further, also why one slopes down and the other slopes up and all of this. But the force is a much more generic concept, and you can imagine if this is a mass, so in engineering we're going to plot it like this, then one force can come from some other mass bashing into it in a collision, but you could easily attach a spring to it or a damper, or maybe some pulley, right? Another weight here. Or a force here. And at this point on the mass, there are all these forces acting. And they all are quite different from this. This is the mass, right? This is the price elasticity. And these things don't really have a price elasticity. So the setup is a lot more general to calculate economic equilibrium. So we have all these different elements. So here we see there are three elements: a mass, a spring, and a damper. And we'll go through all of those, but we'll see that a mass or inertia, as we've already seen, corresponds to demand or supply, right? So just intuitively, if you have a mass, what does it do? Well, it wants to maintain a velocity. When it's standing still, it wants to maintain that. And when it's moving at a certain speed, it wants to do that. What does demand do, the phenomenon? Well, if there's demand for oil, then the demand will want to maintain that. It will be hard to get the demand down to zero or double it. You have to apply some type of force. So the phenomenon of demand, yes?
Quick question. Earlier you said a mass is a price in elasticity. And now you're comparing a mass with a mass. So is a demand the same thing as a price in elasticity?
No. Demand is the phenomena. Really what you have is demand is inertia. Huh? And inertia is the phenomenon. Okay? The mass is a number that assigns a particular value of inertia to a body, all right? Huh? Yeah. And this mass is important because it relates the momentum with the velocity, okay? So all these concepts, momentum, mass, and velocity, they're all related to the inertia, the phenomenon of inertia, all right? Okay?
But is it, maybe this is because I'm viewing it as an engineering problem, but isn't a mass some kind of inertia?
No, yeah, no, a mass has inertia. So a mass is a body that has inertia, and the amount of inertia that it has is measured by the mass. Huh?
So that in the same way you would say that the amount of demand that some good has is the price in elasticity. Is that correct?
Yes, it would be correct, but except for some little details. So if you draw a demand line, this is what an economist would mean a demand, right? A line like this or a line like that, right? This is the whole phenomena. Then this thing here will be the quantity demanded, okay? All right?
Yeah.
And this thing here will be the price. And this thing here will be the elasticity or the inelasticity, okay? Huh? So this whole phenomena has three concepts associated with it. All right?
Yeah.
For us, inertia has associated with it the mass, which is the slope of this line, the momentum, which is the value on the y-axis, and the velocity, which is the value on the x-axis. And this algebraic relationship gives you the same information as this graph. All right? Okay?
Okay.
Now, the confusion is that in most business, the quantity demanded is just called the demand. Huh? So you say, what is the demand for apples? And you say so many apples a day, right?
Yeah.
Okay? So there's a confusion there, and we don't want to be pedantic and say, no, it's the quantity demanded is not really demand, right? Huh? Okay?
Okay.
So be...
That's why you're calling it demand, on what you wrote there on the whiteboard.
Yeah, so officially demand is a phenomenon in economics, but in business, demand is this quantity.
Okay.
That's confusing.
Yeah, okay.
But, you know, it's just that the field is broken up in business, finance, this, and you have all these different terms, okay? Huh? So it's just not fruitful to try to be too pedantic about it. Huh?
I think what we're doing with that the mass also the object and
Yeah.
the property of the object.
Yeah, so you would say, I wanted to talk about that later, right? But this is a good point. What would this be in electrical engineering? Well, the phenomena is inductance, huh? Huh? Right? And that thing itself is an inductor, huh? All right? Right. And many engineers will say, oh, I got a mass here, you know, instead of saying I have inertia here, you know. They'll just confuse the two. And that's okay, all right? And that's okay. Is that okay, Jose? Did I answer that? Huh?
Yes, it's more clear now.
Yeah, it's, look.
It's just the confusion of using the word demand that has two meanings.
Yeah.
Then, I guess.
Yes. We also use the word elasticity in two different meanings. In economics, it's the percentage change, all right? So they will look at dV over V divided by dP over P, and call that the elasticity, right? Huh? Right? Whereas we would, you know, most business people will say, this is the elasticity, right? Huh? And this would be 1 over the mass. Huh? Okay? So this field has got all these little problems, okay? But to tell you the truth, so does engineering, you know? We throw all this stuff in the same term. I mean, you can get a current and you can take the Laplace transform of a current and you call both of them the current, you know? Are they the same? The units are not even the same. Okay, if you have a resistance, you call it an impedance, but, you know, so you're a little bit more careful. But half the time we don't care either. We don't make a difference between the variable and the value of the variable, you know? Huh? So it's just not fruitful to be too pedantic about it. But you know, you just got to keep your head screwed on right all the time, huh? And my experience is that you just get used to the sloppiness that people use, and then in your mind you can unravel it, right? Huh? You know. I mean, we do this all the time. Maybe I'm beating a dead horse, but if I say black is not white, or then it's one way of using is as an equality. And if I say this book is green, it's not that the book is equal to the color green or not equal to the color green. It has the attribute, you know. So, you know, what this is, you know, as Bill Clinton used to ask, huh? Depends on what is means. Okay, so this is definitely a problem in this field, and you just have to get used to it, okay? Just get used to it. Don't be a mathematician or some theoretical physicist that goes nuts in definitions. It just doesn't work, because you start communicating with business guys and they just use it in a different way, you know? And then what? Then you come with your definitions. All right, so a lot of the challenge of economic engineering is to take these precise definitions and then see what the other guys are meaning to say in your terms, okay? Huh? But you can't use our words. You have to then make the best mapping, all right? Huh? So with this notion of a want, which is of economic force, we now know how to we'll be able to figure out how to calculate economic equilibrium, and it's quite a bit more general, you know? So we don't have to look at these crosses and demand lines. You can just take one demand line and then see what forces you can have when you move here or there, and you can figure out equilibrium. You can have a spring, you can have a... so this is what I was doing, right? So you have this inertia. So you can have a system like this. And this will be demand, and then you can have a springiness, right? Usually we call that elasticity, but that will be really confusing, huh? So the phenomena for elasticity is for us the spring here. Let's just call it a spring. All right, and we'll find out that it measures in general the phenomenon of scarcity, right? So the spring will tell you how scarce something is or overabundant something is. Okay? You can kind of see this, like a spring is like a capacitor. It can charge, it can hold stuff. It could hold a commodity or some goods. And then if the inventories are low, you can measure this by the shortness of the spring, and high inventories by the length of the spring, okay? So you get the economic concept of scarcity, and then we have a damper. So that thing is just, they talk also about friction, economic friction. So when you make a model, you have all these, if you make a model of a mechanical system, you will have your degrees of freedom that you model, and those will correspond to various goods or commodities that you're modeling. But there's always a lot of degrees of freedom you leave out. Right, so nobody's going to model in a damper all the individual movements of the molecules of oil that are moving there. And also in your economical business models, a lot of stuff you're going to leave out. And that stuff you leave out is usually put in as friction, you know, transportation costs, this cost, and that cost, anything that generates entropy. So all the unmodeled degrees of freedom go into the entropy, and that becomes friction. So you can see that the notion of a force makes the way of achieving equilibrium slightly more general, right? Because all of these will have their own sort of constitutive relationships, and that's not necessarily a price quantity demanded. For a spring, it will be some kind of force against a total amount, you know, which is different. And for this damper, it will be a force against some velocity, which is also economically different. And we'll walk through the effects of all our linear elements. And why? Because these three linear elements are basically everything. And if you put those together, you can make the most hideously complicated circuits, okay? So this is what we'll start to study. But again, why is demand so important? Why is this idea so important? Because whatever that spring does and this damper does is some kind of force, and the only way of really making that operational is to seeing what effect it would have on a mass, okay? That effect is measured in the change of momentum. In economics, that effect is measured in the change of price, and that change of price is everything, okay? So what does price do? It basically monetizes your economy, okay? You can move around these quantity demanded, and you have a nice exchange economy going, and you can do swaps and trades and all of this, but you won't be able to figure out why people are doing it. They'll be doing it, okay? The why comes from the price that you assign. And the price is measured in euros per item, and that's the first time money comes in. So you can see that this notion of force and momentum, or a want and a price, is the monetization of the problem, right? This is where you add the notion of a price as a driving force. This price and money becomes the driving force that you use to the reason to explain why the thing is doing what it's doing, okay? You start with the kinematics. That's just how the goods are moving, right? Or how the robot arm is moving. And then you add the dynamics, which is the why it's moving. And those are the forces. And that's the money. That's the role of the money. Those are the motivations, okay? All right? So this idea of Newton, of this force, is more than just determining equilibrium. It can give us the entire dynamics, how this thing is moving in time. All right? This is a big, big step. And this is a step that is not very often made in economics. Most economic models are equilibrium models, right? Most engineering models are not equilibrium models, but are about dynamics. How is this thing changing, right? Nobody cares about an airplane that's just standing still on the tarmac, you know, and not changing its momentum. The whole thing is about controlling the change of the momentum of the airplane or the car or whatever, the robot, all right? There's a big shift here. If you use Newton's law and this more general idea of an economic force, that instead of just talking about equilibrium, you now can talk about dynamics. So you can see price as a function of time. So instead of price just being a P, it now becomes a function of time. You could take a derivative of that function, and you'll see how it changes. And those are exactly the forces that act on it, okay? And then you'll know how they are related to the change of the goods. This is the motion of the thing, okay? So now all of a sudden, if you have a few of these elements, you can make time domain models, okay? So then you're doing engineering and control engineering. You can have some big vector X, big matrix A, and you can calculate the derivative of your state. You can identify some inputs, you know, whatever, and you're done. So this is the critical step, right? So taking Newton's law and redefining what you mean by economic equilibrium, by prices, by the price elasticity, gives you a little bit more than a reinterpretation of the dynamics. No, it gives you basically everything, right? Huh? It gives you everything, just like it did in mechanics, basically. Okay, now this idea is not new. To see how you can take Newton's law and use it in a total different field to predict what's going on there. This idea is due to a guy called Maxwell, and one of the greats of physics and engineering. All right, and he had this idea with electrodynamics. So in Maxwell's time, it was pretty well understood already. Even Lagrange and Hamilton was not the case, but Lagrange was how mechanics would work. Quite sophisticated they were in this approach. But electrical theory, electricity was very vague, you know. People knew about electricity, So the ancients knew about it. There was just some charge, and they saw lightning bolts. And then they had these fish. They were electrical, so they get a shock from it, you know. And they knew about electricity. By the way, they also knew about magnetism. You know, I think magnetism comes from Magneta, which is a town in ancient Greece, where they found these lodestones, these things that were magnetic. Okay? And it was just two nice things. And then in the, I think in the 18th century, but predominantly 19th century, guys started to experiment, and they played around with electricity and magnetism, and all of a sudden, I think it's this guy Ørsted was his name, he figured out that if he wove this magnet around a little bit, then all of a sudden he would get an electric current, okay? So here were two phenomena that were totally unrelated, and now all of a sudden he could get an electric current from a magnet, right? Now, it took a little while for one of the brilliant physicists, and his name was Faraday, to sort out what the law was, okay? And what he said was that if you do this kind of business, you induce a voltage that is proportional to the change of the current. This is called Faraday's law. So the voltage, this is the self-inductance, and this is the change in the current, right? Now, this way Faraday linked in a quantitative way magnetism. He called this actually the electromotive force. This particular voltage that you get by swiping around your magnet. So this is how you make motors and dynamos and all this stuff, right? And then Maxwell came around, or I think this was Maxwell, and he says, well, what this is really, one way to look at this is that this voltage is a force, this self-inductance is the mass, and the change in the current is the change of velocity, so that's the acceleration. And all of a sudden he says, well, wait a minute, now I can use Newton's law, and I know what the parallel law is in electrodynamics. And he did the same for a spring. He was able to figure out that that was a capacitor, and a damper, he was able to figure out that that was a resistor that was formulated by his friend Ohm in Germany. All right, so he had these analogs, and he wrote in his treatise, and he gave a bunch of lectures, and he called it the method of the analogs. So you could reason about these electrical systems in the same way as you do about mechanical systems. And the role of momentum, the reason of the motion, is played by magnetism, right? And the thing that's moving itself is the electricity. So they linked it together, magnetism with electricity, in the same way that Newton linked momentum and the actual motion together, okay? And then the magnetism became the reason for the motion of electricity. You could also turn it around, by the way, but you can do that same with mechanics. And then they had something strong. Now, there's a story that Faraday was asked what the point of all this was by a journalist from the London Times. These are very intelligent people. And you know what the guy answered? The guy answered, someday you'll tax this, okay? And he was right, of course. Right? So this whole electrical business is now much bigger than most of mechanics, and it went nuts. And it all came from Maxwell's work on putting these things together. So there's some kind of big table you can make where you have mechanical engineering here, electrical engineering here, and economic engineering there. And this is like a normal force. This is what Newton called the motive force. Newton called this the motive force. It's interesting. It's the motivation for the particle to move, as if it's some kind of economic system already. This is what's called the voltage, or the tension. And the tension already tells you it's like a force, but sometimes called the electromotive force. And this here is a want, or an economic force. And this is a velocity. This is a current. This here is a flow of commodity flow. quantity demanded, whatever you want, a volume. They have tons of names depending on what it is. Right? But some flow of goods. Now, this insight of Maxwell is basically I don't want to say basically the basis of, this is ridiculous, but is the basis of modern control theory. In modern control theory, we want to design controllers that can control any system. We don't want to say, hey, this is a pneumatic system, this is this, we need a different controller. So what do? We abstract away, we make a dynamic model, that's the systems part of systems and control, and we formulate the model in differential equations or you know, AX plus BU format, or maybe in a frequency domain or something like that. And it doesn't really matter to us whether it's mechanical, electrical, or a combination. I guess you guys do a mechatronics projects where they're just combined, right? Huh? And then we just forget about the thing and we design this controller and the thing works, okay? Now, one way to view economic engineering is an extension of this process of Maxwell, that the way we view the world is in these mechanical terms, thanks to the normal kinematics, and Newton, of course, we explained to us what a force was, and we carry that over in these other fields, okay? So in electrical engineering, nobody's ever seen a charge move, you know? In fact, Franklin, who came up with this idea, got it wrong. He thought the plus particles were moving, but they are not. Actually, the electrons are moving, and even that is not moving. It's a sort of momentum, okay? So, but that's not important. You imagine this current flowing through the wire, and the reason why is because you apply this voltage as a force, all right? And then you reason like that, okay? And all your laws are parallel, and you're done. Right? You just see this water flowing or something, all right? And what is an inductor? Well, you'll just see some water flowing and then a big kind of wheel that just keeps pushing it through, right? And what is a capacitor? Well, there's just a big reservoir, you know, with a spring on it, I don't know, huh? All right, huh? And that's the way you got to start thinking of economics. Now, for the flow part, it's pretty easy because a velocity or a current and a flow of goods or commodities, that's not so hard, right? Can get a little bit harder because if these are angular motions, then it's a reallocation or maybe some interest that you collect, you know. It's a little bit harder, all right? But this part, this is the tricky part, the motivation, the economic motive force, right? As being the wants, the willingness, the desires, and all of those that we need to translate, okay? But once we're done, and we've extended this idea of Maxwell. And then if somebody asked me whether I use it as, I could like cheekily say, someday you'll tax it or something. Yeah? That means that you're making some money with it. Okay? So that's kind of the big picture that this effort of economic engineering is in. So you can imagine not only mechatronic systems, but financial mechatronic systems where you have financial aspects and in your otherwise engineering system. And if you build a controller, instead of just controlling for some overshoot of some technical variable, you could try to control the price to stay in a particular area, or you could control profit or things like that. All right? Okay. Any questions about this? Then there's a couple of other things I want to talk about, and I'll spend the last 15 minutes doing that. I got a good question from Chit about the price. And remember, we just defined that in that value-added way. So you go back to the beginning of time and you figure where you are now, and that will be the price at this moment of t. All right? Okay? But there are other ways of determining the price. And for instance, in finance especially, and also in business valuation, they use something called the net present value. All right? Now, what is the net present value? what they do is they'll have some cash flow, right? Here's the cash flow. This seems like something separate, but I want to kind of tell you what this has to do with engineering at the end of this, all right? So this is some cash flow, let's call it, I don't know, F of t, and this is t. So this is just money you might receive at different moments of time. And these, especially in business, they will ask themselves, what is the net present value of this entire cash flow? So what you will do, you say at time 0, right, F0, what is this amount of money worth? Well, 5 euros in cash is just 5 euros in cash worth, right? Huh? But if you receive it a year later, it's worth a little bit less, all right? So you'll have to multiply that by some discount factor. You know, so this is a number smaller than 1. This will be the discount rate. And at 1, this will be E is 1. All right? And at moment 2, you will say, well, E to the minus S times 2. And in general, at moment T, a cash payment at this time is worth, you have to discount it by this amount, okay? Now, what is that whole cash flow then worth? I'll have to add all these contributions up, so the net present value would be the sum of all of these, huh? From now, say I'm at 0 to plus infinity, right? So I just add up the net present value of each item in this cash flow, and I'll get this, all right? So depending on the interest rate, you'll get a different value, all right? Simple. Any bank guy, this is what you learn in lesson 1 of banking, all right? Now, if you step back and look at this as an engineer, you realize this is the Laplace transform, right? This is what it is. Now, this is a moment you always have to like step back and go like, okay, up to now what I've done is I've taken all this stuff I don't understand in economics and I'm giving this engineering interpretation, and now I kind of understand what price is. It's just a momentum, and it's just a measure of how much in demand those goods are, and la 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 la, okay, I get it. But here is a moment that you turn it around. You go like, wait a minute, this Laplace transform, they teach me that. But after my first lesson, I proceed to forget this, and then start looking up tables in the appendix, and then just solve problems. And if somebody asked me how's the Laplace form defined, I wouldn't even know. Huh? I'll have to look it up again and say, what was it, right? And if somebody explains to you what is this equation saying, you wouldn't even bother to answer that, right? And probably a professor neither. Okay. But now you can see how this is, what happens here? You get rid of the time. Why? Because you look at all future benefits ensuing from this. So if this is some economic force, right, you get another notion of price here. You know, this is the units of price. And this was, So this is a different price than the Newtonian price, right? The value added price. This is sort of more idea of value. That's why this area is called valuation. So instead of going from the past and looking at t, you're looking at, well, this is current t. I just call it 0 to infinity. All right?
Do we take the Laplace transform of force?
You can take any function you want. I just put in the economic force here, right? So I imagine the force is the want. There's all these wants that I'm going to have in the future, right? I'm going to want this thing then, and then I want it a little bit more and a little bit less. But the far future, I got to kind of discount my want. They're less immediate, right? My current wants and desires, that's the one I really want, right? So when I put in t as 0, this factor is 1, right? And as I increase t, this factor goes down, right? So what does this thing look like? This is e to the minus st, and this is t, right? So my future wants become less and less important, right? But if I own an asset, I still have control over all these wants in the future. I can loan it out to somebody and this. So what is the total value of that at this moment in time? Well, I'll just add up all these future values and puff, there it is, right?
And what do I do if I just want to look at the future 10 years or 15 years?
Yeah.
That goes into t.
Now you integrate from t is 0 to 10, right? So you just do this, right? Now what we typically do in engineering, we'll always look the Laplace transform to this, but we will multiply this thing by a step or add a, by a step so that this thing falls off to 0, and then you work it out in the tables, right? Huh? You see? But that's just a trick.
Unrealistic to look into the future, isn't it? I mean, forever, because you've got an asset, you've got a value, what you're getting out of the assets, there's got to be a limited amount of time.
Yeah, but this is just a purely theoretical thing. That's just like unrealistic to coming back from infinitely, huh? So normally you will set yourself a horizon, right? And you'll just assume that the flow is 0 from this moment on, huh? That's what you do. So then you can do this integral to infinity. The reason they do this is because this table then looks kind of neat, Because also in engineering, we can look to infinity. It's just more of a theoretical construct, So that's right, but yeah, there is still, there's not, theory and practice are not always the same, right? In fact, as the old saying goes, only in theory are theory and practice the same. But the idea here is to abstract a little bit away from your real problems and say, well, what are these tools that I can use, And how does this idea of valuation match up with something we do? This is what you get in a controls course in your first controls course. You immediately start taking a Laplace transform, and from then on, you don't even bother with time. You just talk about everything as a function of S. And there are lots of, especially electrical engineers, that they've forgotten all what time means. They're only in the S domain, They do everything there. And in the course, we'll be talking about this extensively, what this means. So you'll see that this is now a function of the discount rate. But in the Laplace domain, you see this is a complex number, and in economics, usually it's just a real number, which is the discount rate. So what does this complex number do? This imaginary part can give you the volatility, all kinds of other information, And this S is somehow internal to this valuation. So this is also in business known as the internal rate of return. All right. So it's, on the one hand, we have our ways of setting up time domain models, okay? On the other hand, we have a way of setting up these valuation models. Now, what's cool about this is that it's not that guys in finance or especially Keynesian economics don't use these kind of ideas. I think IRR came from Keynes and stuff, and especially in finance and in business valuation, not in business operation. They use more accounting, time domain things. But in business valuation, these guys like Cunyanis at PwC, these dudes are always in the frequency domain. They're talking about valuation.
Well, actually, every time we do investments,
yes,
we want to look into the future.
Yeah.
Because that's what the value is to the company.
Right.
Maybe, that's where we evaluate.
That's right, but you do it as a separate exercise, right? It's not related to your operations. But now look at what this theory is telling you. It says if you have your time domain model, that's just modeling your operations, your activity, right? I just take a look, and because I have that model, I can predict in principle what happens to the infinite future, to the system, right? Now, if the laws are right, this will be exactly the motion. So in principle, I can carry out this integral. I even know an analytic expression for this force, right? It's just a solution to my differential equations. So I can calculate what the value of this is. So when I have an operational model of my business in the time domain, I can derive from that what the value should be, right? Furthermore, I can say, well, I actually want to reason more in this value domain, and because I want to increase the value of the business, so I want to do some pole placement or whatever I want to do to make this thing as big as possible, or whatever I want to do here, right? Some transfer function or whatever, and then I'll figure out later how I have to run the business in the time domain. Okay? So this is new, the tying together of the two. The one, a time domain model implies a frequency domain model, and a frequency domain model implies a time domain model. There's a one-to-one map because the Laplace transform is bijective. So you can go from the one to the other. So economic engineering gives you two models. An operational model that's more like an accounting way of thinking about things, and a valuation model, which is a frequency domain analog interpretation, or just a statement of the same model, but then in the frequency domain. Okay? And then you can use classical control to do all this valuation stuff. Or you decide like, oh, I want to switch to more operational thing, and then you just use all the time domain models. All right? Then, I don't have that much time left. I wanted to talk a little bit about energy and how that is equivalent to cash flows. I will have to do a rush job if I did that now. So, let me not do that. And respect to you guys that you've already slaughtered through this for a long time. So, any further remarks or questions before we close off the meeting? If not, then I just want to emphasize what I said here. So my goal today was to make sure that you see that economic engineering is really engineering. The math is engineering. We use complex numbers, frequency domain, AX plus B, time domain, blah, 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 all this stuff that only an engineer would understand, okay? Economists will be lost here, now, and probably start objecting to stuff. And so it's really engineering, the whole outlook, the whole purpose, and everything. Then what it is close mapping between concept in economics and the basic laws of physics. And it does that in the same way as Maxwell dealt with electromagnetism, okay? And it's the enormous success of Maxwell's method that really was, for me, the motivating factor to do this. I mean, there is so much more work, there's been so much more electrical systems, especially nowadays, are made than mechanical systems, that it's almost impossible to think what engineering would be like, or even mechanical engineering, where so much electronics is now part of the designs we do. I think there's also one of the successes of mechanical engineering. I was talking to an eminent electrical engineer, and he said, well, what we kind of did wrong was we never put in any mechanical stuff in our electrical things. We just stayed purely electrical. Whereas you guys, you started folding in all this electrical stuff in your systems, and now could make these medical devices and robots and this and that and control theory. And the picture of the whole tour is that with economic engineering in it, not only can we use engineers to solve economic problems, but also we can integrate it within our own mechanical system. So you can simultaneously control both the physical output and the physical forces as the economic forces. So with that, I'd like to end, and then next lecture we'll get in the nitty-gritty of this all. All right? Thank you for your attention here.